graded potentials and really thinking about how they bring about the cellular response. So we're looking at the postsynaptic potentials. And that's the same thing as saying graded potential, right? And so those can be of two different types. So we looked at EPSPs, which is an excitatory graded potential. And this could be resulting from either the positive movement. So this is the positive membrane potential change, which can be brought about by opening, oops, oh no. Opening calcium or sodium channels. And remember, we said that this can also be brought about if we close the opposite type of channel. So closing potassium or chloride channels. Okay. So the major way that we can bring about a graded potential is going to be opening up the calcium channels. This is going to be the main mechanism. But closure of a potassium or chloride channel will actually help to encourage depolarization, as it's going to make it harder for the cell to repolarize or hyperpolarize. So the opposite type of movement is also going to help bring about a positive membrane potential change. Okay. Let's look at the IPSP. So IPSPs are inhibitory membrane potential changes, which are negative changes. So negative membrane potential changes or change. And this is going to be brought about by opening potassium or chloride channels. But also if we close, so closing calcium or sodium channels. Right? So very similar thing as far as the hyperpolarization as well. The main mechanism is going to be opening up our chloride or potassium channels. Potassium wants to leave the cell, so that's going to help to repolarize or hyperpolarize. And chloride is also negatively charged, so it's rushing in is a way to both result in a hyperpolarization or negative membrane potential change, but also this can help to stabilize or reset the membrane potential as well. But the opposite type of movement, closing of the opposite channels, channels that would normally depolarize, can also result in an IPSP, right? And then just to remind ourselves, so just to look at the structure of the neuron. So here's our neuron. Oops. Here's our presynaptic neuron. Axon terminal. Here's our synapse. And then here's our postsynaptic neuron. Okay. So the area that we really are looking at is how the signal is brought in at the axon hillock to result in neural integration. So our action potential moves down this neuron, gets to the axon terminal. This is going to be the synaptic transmission. So we talked about the events of that. which is basically the electrical converted into chemical, neurotransmitter binding, all of those details that we looked at, that will result in different signals coming in. Remember, we looked at what's called convergence, which is where many different signals are coming in through different synapses on this second neuron. Some of these can be positive, some of these can be negative, and they're all going to be assessed. So different graded potentials coming in will be assessed at the axon hillock. Okay. And this is where we take all of those different signals and we assess whether or not they're enough to get us to negative 55. And the entire process of that assessing is called neural integration. Okay, neural integration. So we looked at several different mechanisms of the ways that the postsynaptic potentials can be augmented. So examples were presynaptic modulation. So if we had a modulating neuron, let's pretend we have a, let's say we have a modulating neuron that is modulating this synapse. This can be either encouraging or inhibiting the amount of neurotransmitter released. So this modulating neuron is going to be either resulting in presynaptic facilitation if it encourages more neurotransmitter, or presynaptic inhibition if it blocks or prevents this neuron from releasing excess more neurotransmitter. So this is called our modulating neuron. And that can bring about either presynaptic facilitation or inhibition. So facilitation or inhibition. Now remember, this neuron does not have any membrane potential change here. It doesn't result in a negative or positive membrane potential change directly. All that it does is it signals to this neuron to either increase or decrease the amount of neurotransmitter that is released from this synaptic, from this axon terminal. All right. So just to kind of explain the presynaptic modulation. Another event that we talked about here was the frequency coding. So frequency coding was the ability to either send a strong signal to the subsequent neuron or send a weak signal. And the way that we do that, the way that we differentiate types of signals with action potentials is through the frequency or the rate of the action potentials. And so for that to happen, this neuron would simply increase the amount of neurotransmitter. That would result in more graded potentials coming in faster. So the rate of graded potentials arriving at this neuron would increase as a result of more neurotransmitter being released. So if I had a faster rate of action potentials here, that's going to result in a more release of neurotransmitter, right? Because there's more frequency of the action potential arriving at the axon terminal. That translates to more neurotransmitter being dumped into the cleft. That translates to more graded potentials arriving. And when I say more, I mean faster, right? They're coming in more closely together, which is what's going to translate to a stronger signal on the subsequent neuron. So this is the only way that action potentials can differentiate different signals is by the frequency, and we refer to this as frequency coding. So there's only one magnitude and one amplitude for an action potential, and it's always going to be the same duration. So we can't have a longer action potential. We can't have a stronger action potential. It's always going to be the same amplitude, same duration. The only way that we can differentiate a stronger signal in general is to manipulate the frequency of how fast we fire those action potentials. Okay. All right, any questions on this bit? Any questions? Now, the other thing I just want to point out that would be helpful for you to review before the test is this table. So there are two tables here that I think are really great as long as you know the details of how these three types of membrane potentials differ. So really go over the channels and how each of these events are correlating to the channel and the actions that are happening on the channel. The other one is this. So understanding the difference between graded potentials and action potentials. So you will see questions that expect you to know that, for example, the location of these are different, right? The graded potential is on the dendrites and soma and these sensory receptors here. Action potentials are along the axon. The ions involved are also different, right? So for action potential, the voltage-gated sodium channels are going to be moving sodium and potassium. For the graded potentials, we can have different types of movement through different types of channels. So the ion movement themselves are the same, but know that the receptors are different. So we can have the different types of ligand-gated receptors that can be either ionotropic if they're fast or metabotropic if they're slow. So they are responsible for the graded potentials. And for action potentials, it's going to be the voltage-gated channels, right? So just being able to differentiate the different features of both of these potentials.